the expectation of xy, any moments, the variance, every single one of them that we derived is based on a density, which is a proper function. Now, in practice, do we always have a density when we measure measurements? No. But once you have the measurements, what can we get in terms of visualization? Spherical. Scatter plot, okay. It's just one variable. You want to visualize continuous data. That requires two variables. Okay. What plot could you use? A number line, okay. What plot? Make me proud. Benton.
Why do I have to do that?
You took statistics with me. Okay. Start with the letter H.
Histogram?
Histogram. Oh, you can't do R now.
I forgot the name. I was thinking of something, but something like that.
So in practice, you have a sample. And samples, result samples, just a set of observations. If you go back to the very first week of classes, maybe, I said, what are the derivations that we do? We're going to do in the theoretical sense. They're all parameters. But in practice, we need a sample. So, set of observations, we can always create a histogram. You look at that histogram, you sort of understand what type of distribution you have for the sample. Do you agree? Now, would it be reasonable to use a normal distribution to model the sample? No. Why not?
It's too right skew.
It has a skew, right? So the density curve is going to look like that. So we cannot explain this sample in statistics, using statistical methods with a normal distribution, because that's a skewed distribution. What could work? Perhaps exponential, perhaps gamma, perhaps beta, all kinds of densities. But how do we recognize which one to use? Well, we look at the support. So let's just say 0 to 1. Support of 0 to 1 would tell me beta distribution. Support of 0 to infinity, exponential gamma distribution. So sample would result in a histogram, and we can use the methods, whatever methods that we have. But if you have a sample, we need to find sample moments. If you recall correctly, earlier when I was talking about skewness, I mentioned, well, in practice, if data did not have a skew, we're not going to get exactly 0. We will get something close to 0. So there is a difference between a sample moment and the theoretical moment. So you look at a histogram, identify the skew, then you look at the support, and also you can look at the sample moments to identify what particular model, statistical model or density to use. So we need to find the sample moments. Well, this is how I explain. This is quite informal, but easier to follow. Anytime you see expectation, E bracket, whatever, the E bracket will simply change to No. Good. So that's just how I explain. It's easy to understand. So the E part simply would change to that. And X would become Xi. Does that make sense? Easier way to know. What? Huh? Well, how about this? X and the closed bracket would turn to Xi. Okay. So what did I do? So Xi's are the observations in the sample. What did I do? I simply got the average, right? So this is no longer the actual, this is the actual mu. That comes from the sample, so it's mu hat or X bar. It is an estimator for mu. Does that make sense? So expectation would be the theoretical value that one would expect. Mu hat or X bar that you get from the sample is the sample moment. Does that make sense? So this is an estimator for that. Good. Now that's case one. We know what the second moment is. I'll just call it as M2. What is the estimator for M2? Can you write it?
Same, so it's X minus mu over N.
Oh, it's
X I minus mu.
Xi. No, you're thinking about the variance. No, I just want to write the sample second moment. How would I express it? I wrote the sample first moment that way, or the first sample moment that way. I want you to write the second sample moment.
X times X I.
Okay. Anything else? In other words, what should the expression for N2 hat look like? Use the silly informal explanation that I used with E and the bracket, X and the bracket. He waited until the end to say something about the end, lowercase. Both of them are the same end. Huh? That's okay. I appreciate it. So 1 over n. The expectation part, I'm going to convert it to a sum. All right, look at the x bracket part, the x part. Write it as xi x1. Yes? So xi, x1, x2, x3 would simply be the observations in the sample. And in the frequentist approach of statistics, they better be IID. In other words, every number that I have in the sample better come from the same density, right? Or else there is no point at all in using the histogram doing that. So I can write the third moment, fourth moment in similar manner. If you look at the variance, which is sigma squared, from earlier, sigma squared is simply expectation of x minus mu squared. Correct? Now, how would we write that term using a sample. What would happen to the E part? It'll become a sum. Yes. What would happen to the x minus mu squared multiplied by the square bracket, not multiplied by the square bracket, the square bracket? Xi minus mu squared, right? If you go and look at 2023 textbook, that is what we call population variance. Yes, so this is not the sample variance, rather it is the population variance, which we compute using a sample. Kind of weird. We put it this way because we want to distinguish between this and the actual sample variance that you get from the calculator. S squared is the sample variance. I believe your book calls it as S squared sub n. But just put aside here. And I think the author did it that way because he wanted to demonstrate the sample size n in finding the variance. So this is simply the expectation of x minus x bar squared. Good. In other words, instead of putting the theoretical mean, we are going to put in the sample mean, right? So we call this the population variance because I put in the theoretical mean. But what if you don't know the theoretical mean? You put the sample mean. And this is where things are going to slightly fall apart in a very minor sense. So converting the expert E and the bracket to 1 over n sum I equals 1 to n worked for all of those cases, but it doesn't apply for that one case, the sample variance. There is a concept called unbiasedness in statistics, and you have to get into upper level stats for that. Your book does do a proof. If you want to know more, come to us. I'm not going to do it because beyond the scope of this class. We divide by n minus 1 instead of n because we want an unbiased estimator for the variance. If we divide it by n, it will be biased. A biased estimator is not a good estimator. We want an unbiased estimator. Also, do we remember a t interval? Confidence interval using the t distribution? Yes, a t-test, right? Anytime you use the t distribution, you must have had degrees of freedom. Yes, and that degrees of freedom in a t-test and a confidence interval was always n minus 1. Right? This is where the n minus 1 comes from. Why do we call it the degrees of freedom? Well, now that I had n bits of information, in other words, I had n sample observations, but I computed x bar using those n observations. So I found one quantity using the sample already. So how many bits of information do I have left? N minus 1 to estimate the value of Sy. Hence, N minus 1 degrees of freedom. Does that make sense? So if I use, say, X bar and one more quantity from the sample, then it would become N minus 2. Good. Okay. Any questions?